So we're going to record it there. And I'm going to switch over here to what is called the speaker view. There we go. So again, as I was saying, this meeting is being recorded. This is going to be a review session about buffers. And there will be opportunities for you to ask questions. I'm going to pause it a few times for you to ask questions. And if you have questions about other topics, like I said, please just put them on the chat box or send me a message later. I'll get to it by tomorrow morning. And if we need to, we'll set up a session by ourselves. At this point, like I'm showing you here, let me do something here just so you can see something. I have this alternative screen here, which is essentially a piece of paper with my iPhone camera. Now, you have different options for viewing. So whenever I switch over to this quote unquote whiteboard, I recommend that you go in your gallery and pin this image so that you can see it, or otherwise it's going to look very small and blurry. All right? Okay, I'm back here. So the motivation for this session is that when I was grading your experiment P11, this is the one with the buffers, I noticed a lot of errors, a lot of mistakes. And as I was trying to find out, what I was trying to do was find out, okay, is it that the questions were not clear, or is it that the students' understanding is not clear? So I didn't really get a lot of responses, so I figured out, well, let's go ahead and do this anyway. And that way we cover both bases, okay? So that is the idea. So let me show you what the plan is here for today. I am going to swing over here to my makeshift whiteboard. And again, like I said, you may want to pin this particular screen so that it comes up bigger and you can see what it says. So these are the topics we're going to cover. Working with acids and bases. We're going to talk a little bit about salts, and then we're going to talk about buffers. Now, you know, it's kind of like over the years, I get some experience, and one of the things I've noticed is that this is one of the topics that students seem to struggle the most with. And a lot of it goes back to just not really understanding how to identify who is the acid and who is the base in a chemical equation, and what is it that each one of those performs in the process, okay? So that's why I'm starting there. Then I'm going to talk about salts, because I've realized many times that the word salt is sometimes misunderstood and misleading, and I think students sometimes kind of like get bent out of shape when I throw the word salt out there. They're not really sure what I'm talking about. And then I'll talk about buffers, okay? So let's start out with the first one here, working with acids and bases. So one of the things that I realize is that students sometimes have a hard time figuring out, identifying whether a substance is acting as an acid or as a base or as neither in a chemical reaction. So let's start out by helping us identify, okay, who is the acid, who's the base? And in real life, the simplest way to do it, this is kind of like, I want to say this is a simple approach to it, is to ask ourselves, what happens when you put it in water? This is essentially the basis for the first definition of acids and bases, which was given by Arrhenius. Sorry, I kind of lost it in there, right? And he said that if you take an acid and you put it in water, what do you get? You get hydrogen ions. If you take a base and you put it in water, you get hydroxide ions. And that's the simplest way of distinguishing whether something is an acid or base. If I give you a beaker or test tube with a liquid, and I tell you, okay, can you tell me if that's an acid or base? Well, this is the question you're going to ask. What happens in water? Now, how do I determine that? Well, I think you remember that I started this whole unit before by showing you that the simplest way of doing this is with a litmus paper test. And we saw that acids turn blue litmus paper pink, and bases turn pink litmus paper blue, right? And that was as simple as it gets. Now, we would like to write this in the form of some kind of equation. So technically, the way it works is you have the acid and you put it in water, right? And what happens is you get a something that's going to be an acid minus an H. Let me actually write it there. Minus H. And then you're going to have what's called a hydronium ion. That is a more complicated way because it demands that the acid do something to the water, right? And so based on that, what we did was we said, well, let's talk about what is the ionization equation. What do we mean by that? Well, the ionization equation is essentially this, but written or done in a nice way, done the right way. Let me switch over. Let me zoom in a little bit. Zoom out actually. Right? So let's say, for example, I have an acid, and let's take the simple one. Let's take HCl. Right? Let's take HCl. And I'm going to say, I'm going to put it in water. So I'm going to include water in there. Now, the form of the HCl, it doesn't matter. For example, we know that HCl by nature is a gas. But once you put it in water, what happens is it changes into chloride ions and hydronium ions. Right? This is the basis for the other definition of the acid. This is what we call the Bronsted-Lowry definition. Bronsted-Lowry. And what we're saying is that our friendly acid is transferring a proton or a hydrogen to the other substance, right? So this is going to be a transfer of H. And I put it in quotation marks because we know that it's technically not a proton, but it looks like that when you write out the equation. So that means that if I look at the ionization equation, this is what it's going to say. It means what happens when I put it in water. Now, the confusion sometimes comes because there are some acids that don't behave this way. For example, HF, which is a cousin of HCl, when you put it in water, it also ionizes. Remember, these are molecular compounds, but they are turning into ions. That's what we call it, ionization. And again, we have the H3O plus. But the difference is that whereas every single molecule of HCl was converted into these ions, in the case of HF, you don't have that happening. And this is what we call a weak acid. What does it mean that it's weak? Well, it doesn't mean that it has a low molarity. It means that it has a low ionization. Very few molecules of HF become ions like this. And so what you have is something that we studied before, which is an equilibrium. And in an equilibrium, we have an equilibrium constant. And in this case, we call it the Ka, which would be the product of the substances on the product side divided by the molarities on the left side. And of course, we don't include the water because water is the solvent. It's a pure liquid in this case. So the ionization equation is a way of representing chemically what happens when you put an acid or a base in water. Now, I'm focusing on acids today. I don't want to take us in too many directions here. Now, it is very important that you have the skill to look at a chemical equation and identify who is the acid and who is the base. Remember, we don't typically define in the Bronsted-Lowry method, we don't define the acid or base by what happens when you put it in water, because the Bronsted-Lowry definition is meant to cover situations where water might not even be involved. So the question we want to ask is, what does the acid do? What does the base do? In other words, is something that's based on a chemical activity. Okay, so here I have an equation for you. Please look at it. Let me maybe zoom in a little bit again. You can see it better. And I want you to tell me who is the acid and who is the base in this reaction, just from looking at the chemical equation. Remember, we said acid is the guy that gives away a hydrogen, right? And base is the guy that takes a hydrogen. So what we look for is, we ask the question, who is losing a hydrogen? Is HClO3 or KOH? Well, it looks like this guy here is the one that's losing a hydrogen, because it started out, ClO3 started with H and now it's with K. So that means that that guy there is the one. So therefore, that is my acid. Right? That's how I find who the acid is. I just look at which of the reactants lost a hydrogen. And that's my acid. And so by definition, the other one is the base. In this case, well, specifically in the Bronsted-Lowry equations, it's not the KOH overall, it's actually the hydroxide ion. Okay, let's look at another example here. I'm going to give you another example here. Pull this up a little bit, and let's see if you guys can do this one now. HNO3. I'm going to go this time and again put my full symbols here. Plus CH3NH2. Again, you might wonder, what is that thing? I've never seen that before. Doesn't matter. See, that's the point, is you should be able to apply this criteria to things that you haven't seen before. And let's say that I'm going to get as products pull this over a little bit. Okay, again. Who is the acid and who is the base in this equation? Again, you may have never seen those guys there. But you might cheat because you already memorized some of these guys and you recognize, oh, that's nitric acid. Duh. Right. But I want you to look at the other species here. What happened to this guy? It went from having NH2 to having NH3. In other words, that species gained a hydrogen. And therefore, that means that reactant, therefore, was our base. So that's essentially all you have to do. Look at the equation, ask yourself, who lost a hydrogen? Who gained a hydrogen? We don't have to worry about how it happens or whether the species makes sense or not. No, just look simply at the conversion from having an H to losing an H, from not having an H, having an extra H in there. All right? So that's essentially all you have to do. Let's do one more. This one is going to be like this. Let's start over here. HClO. Let's go ahead and try that guy again. All right. Again, who is the acid? Well, the one that lost a hydrogen. This guy had HClO, and now it's just ClO. Okay, so that's my acid. Who was the base? Well, the one that increased the number of hydrogens. So this went from NH2 to NH3. So that's my base. Now, what's the difference here? This one is reversible. Why is that? Well, because unlike the first example that had chloric acid and the second one that had nitric acid, which you should have memorized, right? Then this guy is not a strong acid. HClO is hypochlorous acid, and therefore it is not a strong acid. So this reaction doesn't go to completion. It establishes an equilibrium. Why? Because very few of the HClO molecules are going to ionize in the first place. And because this is a derivative of ammonia, it's also going to be a weak base, and therefore not many of those molecules are going to ionize. And so you have very little room for these hydrogens to meet up and be added to that guy over there. All right? So things to look for. Number one, who loses a hydrogen? Who gains a hydrogen? Number two, do we have a full forward reaction, or do we have a reversible reaction that ends up in equilibrium? All right. So those are the two big things to look for. But for the moment, the main thing I want you to remember is, okay, how do I tell who's the acid and who is the base? Okay. All right. Any questions up to there? Feel free to unmute your mic or raise your hand in there. Okay. Okay. Let's go to the next one now. Let's talk about salts. Now, when we did the ionization equation, we did it in this form. Sorry, I lost my paper. Thought it was closer. We use this form of the ionization equation, right? In other words, we put the acid as if we were, quote unquote, reacting it with water. But remember, there's like, zillions of water molecules for every molecule of the acid. So it's really not like H2O as a reactant. We're just showing it there so we can trace the transfer of the hydrogen to generate that hydronium ion. But many times for acids, we have a short or abbreviated form, which is simply showing the acid already in water and how it ionizes. Now, whatever this acid is, I put an X in there. What do I know just from looking at that equation? What do I know about that acid? I know that it is a weak acid. Why do I know? Because it has a double arrow. Because it has a double arrow. All right? So again, train your eyes to identify these features when you look at chemical equations. So whether we do it the long form, like we did here for HF, or whether we do it in this abbreviated form, the double arrow is one of the kind of like clues, the hints that we are dealing with a weak acid. So that means that if I make a solution of this acid, whatever HX is, in the solution, I'm going to have molecular form, in other words, molecules of the HX that's not ionized. I'm going to have the ionized form of it and then the hydrogen ions. Now, what do we call this here? What do we call something with a negative charge? We call it an anion, right? But we said that the anion of a weak acid is a base. We call it the conjugate base. Why? Because remember, they're both existing. Now, why is this a conjugate base and not simply an anion? Well, if we say it's a conjugate base, it must mean that it can act as a base. Let's go back to what that means. What does that mean that it acts as a base? What do? Put it in water. So if I take just that guy and I put it in water, it should be able to generate hydroxide ions. How does it do that? It's a base. It takes a hydrogen away. It gets a hydrogen. And what's left over here? Hydroxide ions. Because remember, if it acts as a base in water, it's going to generate hydroxide ions. Now, because it is the conjugate base of a weak acid, it's also going to be a weak base. Notice, the base activity of this particular species, this anion, is not represented by reversing this equation. It's representing by asking, why do we say this is a base? It's a base because when I put it in water, it gives me hydroxide ions. Not a lot because it's a weak base, right? Now, what does it mean when we say the salt of the acid? Remember, we said this is the conjugate base. In other words, it's the product of the acid ionizing, is the anion part that's left when you lose a hydrogen. But what do we mean by a salt? Well, because you got to remember from your Chem 1A or similar class that ions don't exist simply by themselves. They need a charge that is opposite in order to balance out. So I need, in this case, a countercharge. So that means that my anion, as long as it's in water, it's okay. Okay, hopefully you remember from your study of solutions in Chem 1A that water molecules hydrate those ions. In other words, they surround them with their dipoles and they stabilize and essentially block that charge off, even though now the solution is can conduct electricity. But how would I get that substance by itself? How would I obtain well, the only way I can obtain it is if I have something that counteracts that negative charge. In other words, in, or let's say from, an ionic compound. In other words, it could be, with, let's say, with cations. So it could be, let's say sodium plus X minus gives me NaX. It could be potassium, give me Kx. And what is the property that we know about ionic compounds? Physically, what is their physical state? Because of the intense force of attraction between them, and because of the tremendous thermodynamic push to stabilize it in the form of what we call a crystal lattice, these are going to be solids. And that's why we call them salts. So the salt of the acid is simply the conjugate base in the form that we would obtain it normally in nature, which is in the form of a salt, right? So that's where the whole thing comes in with salt. Okay, so again, remember, in the equilibrium of a weak acid, you have an anion that we call it the conjugate base, because if it is put in water, it will generate hydroxide ions. But these anions don't come in by themselves. They come from ionic compounds that we call salts, where the anion is counterbalanced charge-wise by a cation to generate that compound. And because of what we studied in Chem 1A, these are solids, and we call them salts. Do we call salts every single ionic compound? Not really. I think it's typically, we tend to call salts typically those compounds that are formed from, halogens. That's what the word halogen means, salt maker. We typically tend to not call sulfides and oxides salts, but that's a whole different thing. Okay, so that was the second part. Okay, any questions on that before we go into actually talking about buffers? Any questions? Feel free to unmute your microphone and ask. Oh, good. All right. Well, let's put this away. And let's go to our third and last topic. And several things, again, just to keep it simple. What is the goal of making a buffer? And sometimes we talk about them as buffer, just short like that. Or we say a buffer solution, or we say a buffer system. All of those mean essentially the same. So what is the goal of making a buffer? Is to, let's see here, to maintain the pH. Well, a buffer solution has the purpose of helping me keep the pH, with very little variation, right? In other words, maintain the pH. Keep pH as constant as possible. right? Or we can also say in a more active way is to fight off or fend off, fight off a challenge. Let's call it a chemical challenge. Of either acid or base. So I have my nice little solution there. I want to keep it, and suddenly either acid gets added or the chemical reaction you're carrying is going to produce acid. You want to kind of like contain it a bit, or base gets added and or your reaction produces hydroxide ions. You want to contain them a little bit like that. Buffers are very important in biochemistry. And when you saw the lecture, we talked a lot about keeping the pH of blood at a certain constant level between 7.2, 7.4. We call that, excuse me, physiological pH. We know that as we've mentioned, I think, in some other parts, and we'll talk about a little later, enzymes, essentially the major catalysts of most chemical reactions, they have certain, requirements of pH, of acidity, where they can operate optimally. And so you want to make sure that those are kept like that. So if I isolate any of those components and I want to do what is called in vitro work, in other words, I want to study these enzymes outside of the cell or the living environment and into a test tube, I want to make sure that I mimic the conditions under which those enzymes typically work. So I have to design a buffer system to maintain a stable pH so that the enzyme can be studied in a way that mimics the environment of the cell where the enzyme works. Okay, so now we have that. So let's go ahead and see how we make a buffer. What are the components? Well, remember, the components are going to be a pair of conjugates. It's going to be an acid and base conjugate pair. All right. So again, I'm going to use the generic HX form. And we said that if you have a buffer that is weak, it's going to partially ionize into hydrogen ions and whatever the conjugate base is. So this is going to be the acid, and this is going to be the conjugate base. So what I'm going to do is I'm going to go ahead and make my solution. I'm not going to simply put the acid in because it's not going to generate enough of its conjugate base. I'm going to throw them both in, right? I'm going to throw them both in. And we said that we can develop what is called kind of like a modified version of Ka, which is what we call the Henderson-Hasselbalch equation. And that's too long, so I'm not going to write the whole thing here. Sorry about that. That says that the pH of this solution is going to be the pKa plus the log of the concentration of base over the concentration of acid. And what did we say pKa is? Well, this is minus the log of the Ka. So it's the same operation I did to calculate pH with the hydrogen ion concentration. I'm applying that same calculation, but to the Ka. In other words, pK tells me essentially what is the pH of a system in which my acid would be operating more or less, right? So some acids have a lower or higher pKa depending on whether their Ka constant is larger or smaller. In other words, whether they ionize more or less towards the side where the hydrogen ions are. So, and again, this is where sometimes we just basically forget math. All right, so this component here basically says, remember that if I have a log of A over, let's do B over A, right? This is going to be 0 if B equals A, right? Because B over A, if it's at the same, that's 1, and the logarithm of 1 is 0, right? That's just math. The logarithm of this guy is going to be less than 0 if B is smaller than A, right? And the logarithm of a fraction is going to be greater than 0 if the top is bigger than the bottom. So that means this is bigger than 1, which means you have a exponent that has to be greater than 0. Again, that's math. And again, this is where sometimes I think that we get a little kind of like confused because we've forgotten these things. Now remember, in this case, B is the base and A is the acid. So that means that if the concentration of base in my buffer equals the concentration of acid, this one here, this term here is going to be 0. So what's going to happen is the pH is going to be the same as the pKa. All right. Now, if the concentration of base is less than the concentration of acid, in other words, if this concentration is lower than that one, then that means that this term here is going to be negative. And so the pH is going to be lower than the pKa because it's going to be pKa minus something. So the pH is going to be a little more acidic than what the pKa predicts. If the concentration of base is bigger than the concentration of acid, in other words, if I set up my system so that the molarity of this guy is bigger than the molarity of that one, then that means that this term is going to be positive. So it's going to be pKa plus something. So the pH is going to be greater than the pKa. So that tells me something. Normally, when I set up a buffer, I have an idea of what I want the pH to be, depending on the reaction I'm going to study. I may want the pH to be around neutral, around pH 7, for example. I may want it to be slightly acidic, pH 4, pH 5. I may want it to be slightly basic, pH 8, pH 9. And typically, those are the ranges we use for buffers. We don't do buffers like pH 1 or pH 14. It just doesn't make sense because we typically are not working with things that operate in those parameters. Remember that one pH unit is 10 times a difference in concentration of hydrogen ions, okay? Remember, it's an exponential scale. So what does the buffer do? Well, here's how it works. Here's what I'm going to do. I'm going to choose a system where the pKa is very close to the pH target that I have. So if I want to operate at pH 6, I want to get a system that has, a pKa for that particular acid. It has a pKa close to 6. And normally the rule of thumb is plus or minus 1, somewhere in there. How does the buffer system work? Remember, there's two chemical components in here. There's an acid and there is a base, all right? So when I have my acid here and it ionizes, guess what is the principle that governs how a buffer works? Yes, it's essentially Le Chatelier. Okay, let's say that I have my buffer system, right? And somebody throws in a few drops of acid in there. All right. Remember, extra H plus. Where is H plus in this equilibrium? It's on the products side, right? So that means that now my system needs to go back towards the left because that's Le Chatelier, right? I did my seesaw thing. Remember the seesaw? I increased product side, so it needs to come back this way. So system, let's say, moves or transitions. Remember the different words that we used before, right? System moves toward reactants. That's Le Chatelier. Now, who is doing that? What component of this chemical system does that? Well, it's that guy there. Because if I need to remove hydrogen ions, I need a base to take them, right? So my X minus is going to take those extra ions and it's going to, I'm going to use the double arrow, but I'm going to do this one bigger because remember the system's coming this way to generate more molecules of the acid. So essentially what I'm doing is I am causing the hydrogen ion concentration to decrease. So that challenge from the extra acid that was added is counteracted by that component of the system, the conjugate base, doing what a base does, taking hydrogens, taking protons. All right? Now here's the one that's sometimes tricky. What if I add base? Now, when we use these expressions, extra acid or add base, we don't mean changing these guys. Remember, these are weak acids and bases. You can change their concentrations. It's not going to make a big difference because they are weak acid and weak base. So it is understood when I say adding acid or increasing, the acid or adding base, it is understood, right, that we mean throwing in a strong acid in there, like extra hydrogen. Now, what does it mean to add extra base? Well, it means that we are adding hydroxide ions, right? Because that's what bases do. You put a base in there. It doesn't matter what the base was. It could be ammonia. It could be KOH. It could be methylamine, whatever it was. What it does in water, remember, the definition is it makes hydroxide ions. Now, the problem is hydroxide ions are not in here. They're not in the equilibrium. Oh, wait a minute. Yes, they are. Hydroxide ions, the potential here is to take hydroxide ions and remove these protons from here. In other words, it would cause my system to get crazy. And now, because I have an excess and there's not a whole lot of these, the solution becomes basic. So how do I do that? Well, again, if I'm adding base, which of the components of the buffer, which of the, between the acid and the base, which one reacts with the base? The acid. So HX is going to take care of those OH minus ions. And essentially, it does it by donating its hydrogen to them. and neutralizing it. Remember, it's not the hydrogen ion. The hydrogen ion is not a component of my buffer system. It's a product of this equilibrium. But that is the one item that is sensitive to changes in the acidity of the solution. So if I have a base added in there, the hydrogen ion is not going to be, caring about that. The hydroxide ions are going to wipe them out, and then you're going to have excess, right, of hydroxide ions. That's what you're trying to avoid. You're trying to avoid having an excess of hydroxide ions. So the acid of my buffer is the one that reacts with it to generate this. And again, I'm going to, in this case, once more, I'll do this, but technically, because the hydroxide ion is a strong base, and because it's going to be in an amount that is minimal with respect to the concentrations of HX, it'll pretty much go all the way there. Again, Le Chatelier. What happens now? Well, I am using some of this HX to fight the challenge of the hydroxide ions. So that means that this decreases. So now my equilibrium system shifts back towards the left to replace it, and so forth. Remember, the equilibrium is always going to take care of itself. Now, there are some little details, and we've mentioned them along the way. For example, it is obvious that there's only so much that the buffer system can do. And when you did the experiment where you did that graph, you could see that eventually, if you add enough acid or you add enough base, the buffer system gets wiped out and it gets consumed, and it cannot fight off the pH change anymore. So you're essentially operating in a range of concentrations where there's an excess of your acid and conjugate base versus the incoming protons or the incoming hydroxide ions that are challenging my system. All right. So those are things more on a math basis. I don't want to go into that today, but it has to do with this ratio here of base and acid. And it has to do with remembering just the rules of logarithms, how they work, and so forth. Okay. So I think that was the question that tripped, I would say, probably more than half of you in that experiment. The question about, okay, which chemical in the buffer, knows which component in the buffer takes care of the incoming acid or the incoming base? Well, let's remember the components of the buffer are the acid and the conjugate base. The protons are not a component of the buffer, right? Because they're going to get wiped out anyway. Okay? All right. So let me pause here, see if there's any questions. Well, you think about it, because sometimes you have to kind of like process. Remember, you have your, this week, you're pretty much kind of finishing this unit. We're doing solubility, and you're doing an experiment on solubility that you're going to be finishing up. And I think you have another qualitative analysis lab coming along your way, which I hope you enjoy those, because lots of pictures and colors and stuff. We have the exam next week. Now, I have a already recorded review set that I'm going to be posting for Monday, so a week from today. And that one, essentially, there's a PowerPoint that goes with it, and you can download that. I don't know if it's available already. And then I go through some of those exercises in a video that I did in the spring. So it'll be a little dated. But please make sure, what I would do if I were you strategically is try to get all your studying done by Monday. And then, go into that review session, try to do those problems as a practice, okay? Don't wait until the day before the test to try to cover things. I am going to have, excuse me, I'm going to have an extra office time next week. So it'll be the regular one, which is this one on Mondays at 5. I'm going to have another one on Wednesday. And that will be posted in your Canvas and your modules there, your week 9 and 10 modules. And you can check in there what the connection info is. Excuse me. Sorry about that. I choked up. I choked a little bit. But it's not the same connection information as this session. So you have to look it up and make sure you have the correct connection. And my apologies for those of you watching the recording. Some of you are accustomed to other teachers putting all this stuff in Comfort Zoom inside Canvas. I cannot get that thing to work the way I want it to work, and I don't know how to change it. So I basically given up on it. I do my own Zoom session, and then I give you guys the connection information. That's probably about as good as I can get. I think I'm going to scan these things, and I'll post them together with this recording, except I don't know if they're going to make a lot of sense out of context, but at least you can watch the recording and follow along as I do them. Okay? All right. Did anybody have any questions about this last topic here? Agustin?
Not about the last topic, but about the exam, the practice exam, the PowerPoint.
Yes.
I think it's not available yet. You said it's going to be available on Monday?
Yeah.
Okay.
Yeah. And it's not a practice test. It's just it's a review. It's a practice exercises. Cool. So we'll have that PowerPoint and then a pre-recorded Zoom session from last spring where I go over, I don't think all of them, but some of those problems in there. All right, and I'll put an announcement to remind you. Okay, we have a couple more minutes before we stop here. Any other questions? Sure. Okay, guys, we're gonna pause it there. And if you have any other questions, just send me a message. Again, I'll get to it by tomorrow morning. If you still feel stuck, I would say either set up a time with me or also use our tutoring services. So we have free tutoring and they can probably help you out. Not exactly sure what their current schedules are like, but I'm sure you can find out in the connection information there from the LAR, right? Okay, here goes the recording.